All right, now we're going to look at the Bantam PCB. So there's only two PCBs that Bantam has done in this design here. The first one is a limit switch. It's literally just a button with, for some reason, a 4-position connector for a button with 2 wires. Maybe at some point they were going to drive it high and low and they wanted to have an LED. I don't know, whatever. That's simple. I don't think we need to look at it any more than that, other than that the plunger here is just a mechanical button that's being switched. If we pulled up that part number, I'm sure we'd see the repeatability is not anywhere close to an optical limit switch. I'm not going to do that because you know, that's just the way it is. But really, we're going to look here at their Bantam logoed PCB here. All this is it's a open drain type configuration or something. I haven't actually looked at it at all. We're going to look at it. We're going to figure it out together. I did want to point out that the spindle, the reason I wasn't able to get the spindle to work previously was because I was typing in a value that was too low. I think their spindle is rated to like 20-something thousand RPM, which is a whole... I'm not really sure that's necessary in a machine like this, but hey, whatever. It's really a banner spec. So if you can say, oh, we have a 24,000 RPM spindle or whatever the number is, I don't actually know, but it's in the 20K or so. That's, oh, great, because, for high-speed machining, that's great, but this machine doesn't really do high-speed machining. It doesn't have the torque. So to truly do high-speed machining and really cut through stuff at the 200 inches per minute, you need to be able to have a ton of torque, because 200 inches per minute when you're doing this or whatever to do your high-speed machining, your acceleration profile right now with their torque is going to have to be really, really, really slow. I'm not saying the machine can't do 200 inches per minute. I haven't seen it yet, but I'm sure that if you transit the x-axis all the way left to right, there's a very brief moment in the middle probably where you're up to 200 inches per minute. But again, because of the lack of the torque, you have to accelerate there quite slowly. And so it's kind of sad because, this Tiny G V2 board, it has the jerk, the fourth derivative profiling in it. So they've got this really great processor that can do really optimized acceleration profiles. Again, this is not work they've done. This is just Tiny G open source. And that's one of the advantages Tiny G has over Gerbil. Again, if this doesn't make any sense to you at all, I'm sorry, I'll be done with it in a second or whatever. But all I'm trying to say is that the banner spec of we have this really fast spindle is not really high-speed machining, because when you're spinning at 27,000 RPM, again, I don't know what the value is, 28,000 RPM, whatever it is they're advertising, your feed per tooth, so the amount of chip that you're taking off per tooth, requires that you move really, really quickly, because if you can't move really, really quickly and feed that end mill, then rather than cutting, it just becomes a grinder. And you'll know, I haven't actually cut anything yet, but you'll know if that's really the case if the chips you get are just really, really, really tiny. You want chips in a machine like this. You want your chips, ooh, I don't want to get chips near these electronics, but you want your chips to be tangible and feelable and not like Tang powdered, or, insert energy drink in powdered form. So we'll see. Again, I haven't done anything there, but I just can't imagine their motion profiles can keep up with the feed they need on the tooth. And then of course you have the requisite problem that if you're removing, say, 2 thou per tooth per cut on aluminum and you're going at 28,000 RPM, if you're moving that quickly, that's a lot of power. If you're removing 3 thou with a 2-flute end mill, you're going to be doing that 56,000 times per minute. So you're going to be doing that about 1,000 times per second, taking off 2 thou. You can see pretty quickly that you're going to run out of torque on these steppers. Again, all that is to say that to do high-speed machining, which is definitely a good thing on a machine that has the torque, you need the torque. You need it not only in the spindle, you need it in the steppers to actually push into that metal. So anyway, long digression here. Let's, oh, I mentioned the spindle. Sorry. I got the spindle to work. All you gotta do is just do M3, just as you would expect, and then set your speed. Before I was saying S3000, but that value is too slow. Maybe I hit 30,000 there. But anyway, there it is spinning. We're gonna go ahead and just turn it off here. Notice that when I turn it off by typing in S0 or M5, that it's just turning it off. There's no braking happening, which is fine. But yeah, let's go ahead and look at this board. I'm gonna drop down here. and we'll just look again. I haven't looked at this board at all yet, so we'll figure it out together. Let's see. We've got, yeah, just some FETs here. So these FETs are turning on the, right here, this is the spindle driver. So basically, I imagine when you open up the e-stop, or certainly when you open the e-stop, we're opening everything, but also when you open up the door, I think the spindle will probably stop when you open the door. So I have just put two jumpers in here for the e-stop and the door being open. So this is the door here, and we can take it out, and Bantam would tell you that the door is open. So what I'm gonna do, yeah, my guess is here is that when you open the door, the motor becomes unpowered, and we can of course probe this. I'm not going to probe it because I don't have the probe in screen now, but what I'm going to do is I'm just going to start the spindle right now at S5000, I think. Let's see, M3. Okay, so the spindle is spinning now, and I imagine that when you open the door, which this switch opens the door has now been opened. Yeah, so as soon as the door opens, the spindle stops. However, motion is still allowed on the gantry, and we're going to say X minus 50 again. So yeah, motion is allowed on the gantry X, Y, and Z when the door is open, but the spindle is not allowed. So interestingly here they've got, do they have an isolation on here? Yeah, this could be made a lot simpler if they were actually cutting the low side instead, because right now they're having to translate up to the high side. I'm not going to go too much into the detail there. I'll let their engineers figure that out. But if you have an open drain on the low side and you're just cutting off the ground instead of the positive, that's much easier to do from a electrical standpoint. They're doing the exact same thing over here. They just have it in duplicate because they are trying to share the current that this motor is going to accept. The spindle, of course, takes quite a bit more power. We determined before that we're only sending about 10 watts here, and we definitely were able to turn off the power supply, which is at least 400 watts. So most of the power is going through here. Yeah, okay, cool. You know, one odd choice here, I don't understand why they have these two negatives ganged up here to the one. Obviously, I understand it because the motor controller here is off the shelf, but I don't know why they didn't just take this thicker gauge wire and route it all the way to here and just have a much larger connector. That's just an additional cost that they didn't necessarily need, especially because this is double heat shrunk there. Okay, so what else are we doing on this power board? Of course, this is the logic basically to turn this FET pair on and off. There's equivalent logic right here that's routing back over to here. And again, it's just a little voltage translation circuit with a little capacitor to keep the noise down. So not a whole lot really jumping off and on there. Oh, are we generating 12 volts? Why? Oh, because that's running the LED board. Okay, wow. So this whole circuit here is a very poorly laid out switching power supply. Anyway, so we're generating 12 volts literally to power this LED board. I don't think we're using it anywhere else. We might be using it on some logic, but gosh, what a waste. And again, this is just really, really poorly laid out. Yeah, like terribly done. And I think it's actually not even fully synchronous. I think that we have an inductor here, and this is just a flyback. We can see, again, we've got, yeah, this is absolutely a flyback. So this is an unsynchronized or non-synchronous power supply. And this is actually a variable frequency power supply to keep the noise spread spectrum to lower emissions. So yeah, this is just our switcher here. And man, these parts should be a lot closer together really to keep that noise down. And look, they're using this tiny 0402 over here. So whomever is building this board for Bantam, maybe they're building it themselves, is probably charging them for this tiny part for the whole thing. So there's probably a little bit of a price adder there. I don't know why on earth. That was probably failure to look at the part number, and they were just like, oh, we need a 10 nanofarad cap. But yeah, everything else in here is quite large. You know, is 0805 and larger, and then there's just this 0402. 0402 is actually kind of difficult to place on even the kind of the like Seed Studio type stuff. They'll obviously do it, but if you can do 0603, that's certainly better. Of course, you can go down to like 02001. I've definitely done designs that had 02001. That's about 8 times smaller than this, probably maybe even a little bit more than that smaller. You can't even see 02001s without a magnifying glass, really. But they definitely have their place. And then, of course, yeah, there are a few more over here. Sorry, I missed those earlier. I think my finger was covering them. But yeah, we've got a few more parts over here that, again, could have been 0603 or larger 0805 even. And then you got some parts that aren't populated. This is just transistor logic here. You know, the e-stop being pushed or not. I had kind of ventured a guess earlier that when the e-stop is removed that LED was going to turn on. It's backwards, basically. When the e-stop is engaged, the switch turns off. So actually this is negative logic. It says e-stop, but really it's when the e-stop is not engaged that the LED turns on. So this is the running position right here. So yeah, this is a painfully simple board. All the control is coming in through here, and it's labeled e-stop is certainly there with an F, e-stop F. I don't know what these other two signals are. I don't really even care. They're basically just this is a very, very simple board. You can see they have a pull. Sorry, I'm out of frame. They have a pull down here so that the when this is disconnected, when you have the door open, this is pulling it down. They presumably have another one for the e-stop because it is required that if the e-stop is not connected, that it be engaged, which is actually is the behavior I'm seeing here. There are some diodes here. This is probably it looks like a Zener diode. I had actually complained earlier that there was no Zener diode on this board because when you move the gantry, the back EMF from the stepper basically drives back through this board into here, back through here, and then it actually was turning the power supply off. But there is actually a diode here. It's probably not the correct value, and it's going to basically, when you exceed a certain voltage, it's going to break down and start conducting current. It becomes a flyback diode, though, when you start injecting power. This is supposed to be consuming power that way, but when you move the gantry, the power actually comes back this way. This DRV8818 actually works both directions. When you are moving the gantry, it actually is generating a back EMF, and you can actually charge like a battery, for example, not with this circuitry here. But so I'm done looking at this board. It is just painfully simple. It's literally power in, power out, some FETs to switch the power in on the high side for some reason, even though it should be on the low side. I know I've been complaining a lot on this device. I don't always complain about everything. There are actually things that I really, really enjoy, but this has not been one of them, unfortunately. But hey, let's rip on Synthetos for a while. Okay, so this board here is the Synthetos G-Shield board. It's made by the same company, and you can see on this board that they've placed these 100 microfarad caps on here, and that's because these stepper motors are choppers, and they actually pull quite a bit of current. They have a very high DIDT when they're chopping on the steppers, which they're always doing when they're energized. And so you want these to be very close, and you actually want closer capacitance as well. I'd always had some minor complaints that this didn't have capacitors closer. If you look at a very similar board, I've already shown it twice, but I'm going to show it again here. This board is an older board, but it's still good. If you look here, we've got the same 100 mics, and they're hiding out here under a heatsink, but they're there as well. But then we also have some local ceramic capacitance here. I believe that's a 22 microfarad cap, just to be really, really close to the VN. The more you do that, the more oomph, the faster the DIDT can be on your chopper. This board is not great, but this board doesn't have it at all. So look, this is the V9 Synthetos board. Look at our capacitance here. So we have a capacitor right there. Let's look at their local capacitance. And, ooh, no, there's some problems. This capacitor is no presento at all. The only capacitance we have on a local level is a really small 0603. It might be 1 microfarad. That's not enough for the DRV8818s by a long shot. And so, oh wait, hey look, this cap here, that's 24 volts obviously, but man, it's a long way away. It's maybe close to here, but an electrolytic aluminum this large is definitely going to have some ESR to it. And also, the further you get away to these motors, the less impact that this has. So if you store 1,000,000 gallons of water 1,000 miles away from you, that's not very useful. If you store 10 gallons of water to where you can just grab it and drink it, that's going to be really useful for you. This guy over here, this poor little helpless chopper here, is trying to step these motors, and it's having to say, I need water, and it can't get it. Of course, we're actually talking about electrons. But all I'm saying here is that I thought that these capacitors were kind of too far away, and there wasn't enough local capacitance here. But this is a different ballgame altogether. Especially the X drive here, which is the gantry moving left and right. That guy's real far away, and then I presume this is Y, which is this axis probably the most affected because that's moving the whole table, and then I imagine this is probably Z. And Z is still pretty far away, and there's actually a dead bug on this PCB here. I don't know what it's doing, but it's definitely tapping this positive. I can't help but wonder that it's actually adding an intentional ESR for some reason. I don't know why you would do that, but let's see what it's measuring. It's measuring the same 24 volts, so I think that we're adding an intentional ESR in there. Of course, we could turn this off and measure the resistance there. It doesn't matter because this is already too far away. Anything they're doing here is just making it too further away. They need to have these 100 mics. One here, one there, one here, and one there. And not this header here. This should be much further away. This is doing stuff over there. So the Synthetos implementation, you know, I love the work Synthetos is doing on their Tiny G and I guess the original. You know, another issue I've had with this PCB, which was this was not in the Bantam, but it's made by the same company. They have actually hooked up one of the pins that should be grounded. They've actually hooked it up to 24 volts, and it actually causes a long-term issue with these DRV8818s. I hope they fixed that on this board. I haven't looked yet, but I submitted this as a bug to the G Shield V5 in 2015 maybe, and they basically said we're not going to fix it. So you know, it usually works, but when you start sending thousands and thousands of these out, sometimes they break, and it also makes them a little bit less fault tolerant to manually moving the axis here. So this is the reason, man, long explanation, but this is the reason why when you're moving the gantry, you can actually cause the power supply to turn off, because what's happening is you're generating a back EMF in here, and this driver is having to try and salvage itself. It doesn't really want to do that, but it has to, particularly when it's not enabled. It has to feed that voltage back to this power supply, but this is so far away that once it's finally pushing it there, this voltage gets much higher. It back feeds through here, and it comes through here where we're not actually monitoring current in any way. And it causes the voltage to come straight through these FETs, go right back into the power supply because nothing else is consuming it. And there are no other consumers, right, except for this light bar, but it's running at 12 volts. And if you had a fan and a light bar, or if you were literally just dumping heat into a large resistor somewhere, you'd be a little more fault tolerant there. Or if you had a crowbar of some kind where this would break down faster, or if you had a FET that could actually modulate. So that would be the real ideal solution, is you'd put a FET with a 10 ohm resistor or whatever. It'd have to be a pretty beefy FET. It's like this 8 SOIC is probably not large enough, but you could certainly put a larger, gosh, look how much room is left on this PCB. You could certainly put in here, and when you sense that back EMF, you could basically short your phase to ground, or you could just re-energize the step here. There's a ton of ways you could fix this problem, none of which have been addressed. So anyway, there are some hardware limitations on the electrical front here. Anywho, this schematic is unavailable. This is my final gripe here on the electronics here, and again, nothing to do necessarily with Bantam, except that by shipping a commercial product, Bantam really should be able to reproduce these schematics. And it seems that Synthetos has not released these schematics yet. Even though this V9 board, there's murmurs of it online starting in maybe 2015. And then, of course, they're saying it's not a released product yet, it's not a released product yet. Well, now Bantam is shipping it in a released product, and we still don't have the schematic. Of course, we have the Tiny v2 firmware. We checked that yesterday. It was like 0.99 or whatever. But yeah, I'd really like to see some of this open source stuff be a little more open source.